So welcome. This is the second class for derivatives. We're on page 12. And I just quickly recapped, without the recording, some key stuff. Basically, if you have the limit as x approaches some number, generally you're going to try direct substitution and then we're going to factor it. If you have x approaching 0, which is still a number but kind of a special number, sometimes you need to use Desmos, or I'm going to allow you to use Desmos to make it easier on you. And then as x approaches infinity, as x gets very, very big or very, very small, we can actually work that out with algebra. So I said this yesterday, but I'll go into Desmos. This topic, this area of the notes is called limit as x goes to 0. So what happens as we get closer and closer to 0 for things like these functions? Okay, 1 over x, 1 over x squared. Well, I don't actually need to use Desmos for this. I can just look at this. Just look at this graph. This is the graph of 1 over x. As x comes towards 0 from the right side, I'll just zoom right in. This is the function 1 over x. As we get closer and closer to this 0 point from the right, what happens? Well, it's shooting off to infinity. I'll tell you that for free, positive infinity, okay? As you get closer and closer to 0 from the left, it shoots off to negative infinity, which is why when we get the limit x approaches 0 of 1 over x, it actually doesn't exist. Okay, so that's what it's talking about in these notes. And that should make sense. Think of it this way. If you have the limit, let me make this a little bit smaller, as x approaches 0 from the right, 1 over x, imagine it being 1 over some very, very, very tiny small positive number. And if you divide 1 by a very, 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 very small number, for example, put in your calculator 0.000000000000001, it will give you a huge number. And it'll get bigger and bigger the smaller number you put in. So that's why we get positive infinity. From the left, it works the same way. The limit as x approaches 0 from the left of this, it's 1 over some tiny small negative number, which is going to explode again, but it's going to be negative, which is why the limits don't agree. Remember the limits on left side and right side need to match. They don't match. So the limit doesn't exist. Okay. Everyone who's in here now, could you just type hi? You're not going to distract me. I'm getting a little bit of extra push to make sure that the students who are there in the chat are actually there in real life, not just their computer. So just type a little hi so I can see you and also tell my boss that everyone's coming to my class. So let's take a look at this. We could easily graph this in Desmos as well. Hi everybody, nice to see your chats. You're all alive. I feel famous. I've tricked you. That's why I want. No, anyway. So let's look at 1 over x squared. If we graph that, I'll graph it for you just to prove you that this isn't that hard. Ooh, spoiler alert. I'll make a new tab here. Desmos. 1 over x squared. You can do it easily, really. Just bring up your calculator, bring up Desmos, and of course I say it's easy, but here, 1 divided, oops, Surface, stop it. 1 over x, stop it, squared. Go away. Okay. Sorry about that, fighting my computer. What we see here, this is the function 1 over x squared. Let's just follow a point. Let's follow this point. Okay, as we go to 0 from the right, look at those y values. They're shooting up, 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 up. Oh, it even explodes. It literally jumps into space. And if we zoom out, of course, it's going towards infinity on both sides. So from the left, from the right, it both explodes to infinity. So that's our special case here. If we have squareds, 1 over x squared, it's going to go to infinity from both sides. So the limit does exist. From the left and from the right, it exists. Okay, it explodes to infinity. So I'm not going to oversell that. I'm just going to very quickly write what the answers are. Because I know what the graphs look like, and you could work it out algebraically as well, but I'll do the shortcut method. This graph, A, would look like this. And so as x approaches 0, it explodes. It goes to infinity. The limit does exist, and it equals infinity. Okay, you could graph it on Desmos. If you graph this one on Desmos, the graph also looks like this. Okay, and so in this case, the limit does exist as well. It's infinity. Remember, we're dividing by a tiny number here. So of course, it should make sense in a way that it explodes. I don't trust that one. I don't think that one's right. 2 over x cubed. I think 2 over x cubed looks a little different. So I'm going to graph that. 2 over x cubed, 2 over x cubed, 2 over x cubed. Aha! I was right. One's negative infinity, one's positive infinity. So it doesn't exist. Sorry about that. It doesn't exist because the sketch that I made earlier is not right. It actually looks like this. It shoots up to infinity and down to infinity. The limit at 0 doesn't exist. I'll give you a shortcut for all these in the very end. This one, what does it look like? It looks almost exactly the same. It looks like this. So what's our answer? Our answer is that it doesn't exist. And finally, this one here looks like this. What's this answer going to be? Little test for you. What's it going to be as it goes to 0? Remember 0, we're looking at x approaches 0. That's this center line. Infinite. It does exist because both sides are shooting down to negative infinity. So it's negative infinity. You're allowed to have infinity as a limit because you're explaining what happens as the x gets closer to where it wants to be. You're just not allowed to have two different limits on each side. All right, negative infinity. So Ahmed, everyone who said positive infinity, if you said positive infinity, make sure it's negative infinity. Little shortcut for you. Shortcut. If you simplify the expression and it has 1 over x even form, you know, some number over even, it doesn't even matter what's on top, you will get infinity, or if the number on top is negative infinity, right? If there's a positive on top, you get positive infinity. If there's a negative on top, you'll get negative infinity. Okay, I'm just trying to show you some shortcuts. So look at this, positive 7 over an even number, infinity. Negative 5 over an even number, negative infinity. Okay, just giving you some shortcuts. If you don't catch it, just make the graph or work it out. The extension to the shortcut, plus or minus x over an odd number, x to the power of some odd number, it actually works out to be that it doesn't exist. So if you see an odd number, for example, you see an odd number here on bottom, once it's been simplified, it doesn't exist. Okay, that's your shortcut. You don't even need workings for that. All right, so I'm gonna move on because we have lots to cover today. Well, I won't move on. I will give you a chance. Do you have any questions on that? Any little ideas or problems you have with that you want me to re-explain? I don't mean to go too fast. Sometimes it's hard to tell. I know it's early in the day, but okay, let's move on then. As limit goes to infinity, limit as x goes to infinity, that is not the same as what we just did. What we're doing now is instead of the limit going to 0, we're going to some massive number. So as x goes all the way to the right, what's the function going to do? Or as x goes all the way to the left, what's the function going to do? Well, it's actually pretty easy to work out. I'll tell you the rule and then I'll explain it. The rule is that as x approaches infinity, it doesn't matter what the power is, it's always going to go to 0. So let me give you an example. What's the limit as x approaches infinity, some giant number of 1 over x squared? Well, it doesn't matter what that x is. What matters is it's 1 over some giant number, some big positive number. So maybe that number is, I don't know, 99999999999. You can just put it in your calculator if you want. Make the biggest number possible. Set up a fraction and just say 1 over 99999 squared, because that's basically infinity squared, right? So just get that, and what do you get? The calculator gives you back, in my case, 1.000000002 to the negative 14, 10 to the power 14. It's 0. So imagine taking 1 divided by this massive number. Of course it's 0. Big numbers, or sorry, numbers divided by a huge number, it's going to be 0. In the notes here, it says the bigger we make x, the smaller we make the fraction. So it approaches 0 as we do this. So that should make sense. You have a giant number on the bottom of the fraction, it's going to basically squeeze it all the way down to 0. And if we have the limit as x approaches negative infinity of, say, 1 over x, doesn't even matter what the number is, 1x to any n, any number, that's going to be 1 over a big number again, but it's going to be 1 over a negative big number. So like negative 99999999999, right? Negative 999. You can put as many nines as you want. I mean, literally, put it in your calculator. 1 over 99999. 1 divided by negative 99999. It's essentially 0. So we can say it goes to 0. There's no such thing as a negative 0, by the way. It's just going to be 0. Okay, and that's our rule. So long story short, if you have an x on bottom and it's going to infinity, it disappears. Let me show you what it looks like. On the graph, this should make sense. This is our x equals, so x to the power of x to the 3. So there's an x on bottom and we're going to infinity. Should be no surprise what happens here. Oops. As we go to bigger and bigger x values, what's happening? It's going towards 0. It's basically 0 down here, right? That's what I'm talking about. From the left side, if we go to negative infinity, so go left, tell that story. Negative infinity also flattens down to 0. Let me show you what it looks like with math. This is extremely important, this little note, and you'll see what it means very soon. It says to evaluate limits as x goes to infinity, where x is in the top and bottom. So what it means is, like, maybe you have x squared plus 3, and you had like x cubed minus 4x or something like that. Something weird. What you need to do is you just need to look at the highest power in the denominator, and we're going to divide everything by that. Look at the highest power of x. I'm going to divide every single thing by that. So let me show you what it looks like. That'll make our life really easy. In fact, this is one of the easier limits to get once we get to where we want to go, of course. So, all right, if you're not following me, that's okay. Just pretend that you just started. Let's look at this function. Tell me, what is the biggest value of x in the denominator? What's the biggest power of x here in the denominator? What's our important thing? The 2, so I thought someone might say that. It's not, oh, sorry, yeah. I thought you were talking about this 2. We're talking about this 2. So we need to take this piece. That's the highest power. Highest power on the bottom, the denominator. We're going to divide every single thing by that. So we're not looking at the constants, okay? The 2, the 3, these make no difference. No one cares about those, obviously. Those 2s and 3s, they don't matter. It's the power of x. It's not in front of it, the power, the one on top. Oops. So let's just look at the limits. What happens to the limits? As x approaches infinity. Imagine dividing everything by x squared. So let me just take this top one. What's x squared divided by x squared? You can do this in your head. What's x squared divided by x squared? It's 1. Okay, so that gives us 1. Do the next one. What's 1 divided by x squared? Well, it might look complicated, but it's going to end up very simple. It's 1 over x squared. How do I know that? Because I'm taking this 1. What's 1 divided by x squared? it is that. There's nothing to do. There's nothing to simplify. So that's why I'm going to put that here. Okay? What about 2 over x squared? What does that give us? It just gives 2. What does 3 over x squared give us? It just gives 3 over x squared. Okay, before I go any further, do you see what I'm doing, or am I just doing craziness for you right now? I want to make sure that I haven't lost anyone. I can't listen to my own brain, right? So sometimes I need to know. Do you see what I'm trying to do? I'm dividing everything by the biggest term. They're canceling out, and I'm getting a simplified version of it. Okay. Let me show you why I'm doing this, because some of you are like, why make it harder? We haven't done anything. Well, this is why. Let's look at every single piece. Remember, let's just zoom in here. We want the limit as x approaches infinity. What's the limit as x approaches infinity of 1? Well, it doesn't even make sense. There's no x there. It's going to be 1. What's the limit as x approaches infinity of 1 over x squared? Well, we have 1 divided by a number that's getting bigger and bigger and bigger. So it's going to be a tiny, tiny, tiny small number. So we call it 0. And that's why we do this. We're allowed to sort of work out what infinity would be. Let me show you this. This is it's 1 divided by a big positive number. So what's 1 divided by any giant number? So take 1 on top, divide it by 9999999 squared. It's 0. So 1 over 0. Let's keep going. What's 2? 2 is still 2. What's 3 divided by the biggest number you've ever imagined in your life, plus 1? It's 0. And so the answer is 1 over 2. So this is the full picture. This is how we approach these. They're very easy. If you're finding this is difficult, you've probably missed some key information here. It should be very simple. We're just evaluating the limit. And if you have 1 over x form, if there's an x on bottom and we're going to infinity, it becomes 0. Okay? So this turns into that. This turns into that. Okay, clear? I'm going to assume yes. I want you to try one of these questions on your own. Before I do that, just very quickly, some students find it very helpful, just from the start, this is just on the side. Instead of doing it in your head or on the side of the paper, some students like to do it this way. Just imagine everything multiplied by the smallest factor. I don't like to do it that way because it's too much on the page, but if you want to, you can think of it that way, and you multiply, and you multiply, and you multiply, and you multiply. But for me, in my opinion, that's a longer way. Why do more work? Okay. Let me do one more example, because I don't need to do many of these. First of all, let's do a better one. Let's do D. They're all the same. They're all the same. Let's do D. What is the highest power in the denominator? 5. It's this 5. We see a high power of 5, not 3, not 4. Those are not as big as 5, obviously. Just look in the bottom and look for the highest number. We take that value. Divide every single term in the fraction by that. And you don't need to show work. There's no reason to show work. It would, notice this is negative infinity. It would just slow you down. What's 5x cubed divided by 5x to the 5? I will show you work. I'm just telling you, you don't need to show it yourself. 5x cubed divided by this x to the power of 5. Just subtract the powers. That gives us 5 over x to the 2. And if you want to think of it this way, just take the bigger number, subtract the smaller number, and keep the bigger number where it was. So for example, if you had x to the power of 7 over x to the power of 12, what's 12 minus 7? 5. It'll just be 1 over x to the power of 5. You can work on that. It's just basic exponent rules, yeah? So what this gives is 5 over x squared. What's x divided by x to the power of 5? It's 1 over x to the 4. What's 5 x to the power of 5 divided by x to the power of 5? It's just 1. And then we have to be careful with this one. This is 4 over x. So again, I'm telling you, you don't need to show the work for this because they can be done quickly, but obviously still be careful. If you need to show all the steps, show all the steps. So before I go any further, am I making any sense to you or am I not? Yeah. So you're not allowed to take the power from the top. I'm not going to explain why because it's a little bit weird and it's not worth talking about. You have to take the bottom. It won't work out the same. Sometimes it works out the same, but sometimes it doesn't. It'll always work if you use the bottom. Okay, so every time the bigger power on the bottom, yes, exactly. So let me go up. I want to make a very clear note here. On page 13, there's actually a typo. It says that you need, look, under the highlighted part, start by dividing both the numerator and the denominator by the highest power of x that appears in the denominator, is what it's supposed to say. Whoever typed this typed it wrong, but denominator is your key point here. And there's a little typo. Okay. So this is very fast. Once you've done the first step, the rest follows. This and this and this are all 0 because we're going to a giant number. So dividing by doing some giant number here. It's 0 plus 0, 1 minus 0. They all go to 0. They're all being squashed. You're dividing something. It's like you have one pizza and you're dividing it into 100 billion pieces. Well, no one gets any pizza then because you've divided into such pieces that you might as well be eating air. That's what it means. This is 0 over 1. What's our answer? What's 0 divided by 1? Do not tell me error. Don't tell me error. It's not error. It's 0. No one did. No one said error. Maybe I said it first. But it's 0. And check it on your calculator if you need to. 0 divided by 1? 0. Right? I'm trying to give you tips to make sure that you are clear here. So once again, if you have a x on bottom here, and you're going to infinity, it's just going to squat it down to 0. It doesn't matter if it's negative infinity or not. Right? I said I'd give this for homework, and let's do one more. Tell me what the answer to the B is. What's the answer to B? Let's see. You can try it yourself, or you can write out what I'm doing. I'm just going to try it myself. Oh, you lost it right at the end, yeah? 1 over 2. Okay, I skipped a step there because normally I like to evaluate limits in a separate step, but this is the idea, okay? So let's just be confident that if we're going to infinity, those are usually the easier questions because there's not a whole lot of algebra you do. You just divide by the biggest power on the bottom and you're good, okay? So I need to move on. I spent half an hour exactly on that, which is what I wanted to cover at the end of yesterday's class and didn't get a chance. So let's see if I can pick up the pace. All right, hold on to your butts. We have a little bit more theory to cover. The rest is the start of the practice section. All of those answers are online, or I'll put them online. So any one of these I could ask you, except for challenge. Make a note that on page 15, F is a challenge question. It's a little tricky. I would never ask it on a test. I think there's maybe another challenge in here, but just keep them the same difficulty that I've been giving you this whole time. I can come back to that before the test and review if you want. But we got to move on to page 18, the derivative. So, does anyone know what the derivative is? Has anyone ever heard that word? Have you done pre-calculus, or is this the first time you've ever heard it? Some students they've seen it in high school. A lot of students haven't. The quickest way I can explain the derivative right now, the derivative is just the slope of some function. If you have a function, if you know its derivative, it means you can get the slope of it at every point. You can figure out the steepness at any point. So we'll get to that. Let me just go back through some basics. So first things first, the slope of a straight line. And because derivatives are related to slope, we need to talk about slope. Well, the slope of a straight line is simple. We know that to get the slope of a line, we just need rise over run. Or some students like to call it, they'll do y2 minus y1 over x2 minus x1. But the whole point is just, let's look at this graph. Let's get the slope. I'm going to choose any two convenient points. I'm going to choose this one and this one. You could choose any 2 points. You could choose this one and that one if you wanted, or whatever. I like to make my life easy. And then if you want to do rise over run, the rise, this is the rise. It's a difference of 1. It's risen by 1. And the run here, how far have you gone? You've gone 2. So this is the fastest, in my opinion, this is the fastest way to get the slope. If you want to do it by math, you do y2 minus y1, x2 minus x1. What's this point and this point? Give me the coordinates for these points. Well, the first one is 0, 1. You've done way harder things than that now, so that should be easy. For the second point, this is 2 and 2. The reason I'm writing those is because this will be the first one, x1, y1, x2, y2. And we plug those in. This is review, which is why I'm not really going through it too heavily. y2 is 2. y1 is 1. x2 is 2. x1 is 0. 1 over 2. So y values, x values. Basic slope stuff. So hopefully you remember what slope means. So the line is not too steep and not too flat. The bigger the slope, the more like this it is. That's all we're talking about. All right, have I lost you so far? This is like high school stuff. This is junior high. So if I've lost you, I'm very, very sorry, but it's going to get harder. Okay, so we just calculate the point between 2 points. A new piece of terminology is the secant line, and it's just a fancy way of saying the slope of a curved graph. Instead of it being a line, like clearly we can see that this isn't a line, it's a curved line. We just take 2 points on it. So for example, in this case, it's taking this point and this point. If we draw that line, it's called a secant line. And what I like to think, any 2 points, yeah, because for the secant line, we're getting the slope at different parts of the function. So we might want the slope at this point. We're just getting average slope, because a curved line doesn't have a specific slope, at least not that we can tell yet. what I like to think of it as cutting out a section of the curve. And I think of section because secant lines, when you cut through the curve, it looks like it leaves this little like cut piece. But the point is, curved lines have different slopes depending on where you are. Look at this. If I get the slope here, it's different than the slope here, which is different from the slope here, which is different from the slope there, which is different from the slope there. It's got 5 different slopes. So we just take 2 points and get the slope of that. So for these 2 points, we have, I'm just going to do rise over run. You can do it whatever way you want. The rise here is, the rise is 2. And the run is 1, 2, 3, 4. That's 2 over 4. So the slope, once again, is 1/2. If we took 2 different points, we would have a different slope. So Abdulaziz, you said any 2 points? Yes, but also no. If I ask you the secant line, I'm going to give you the 2 points, and you tell me what the slope is. Okay. In y-intercept form, I'm actually, we don't need to worry too much about the different forms, but I will just remind you, there's 2 forms that lines can take if we wanted to find the actual line itself. Slope, y-intercept form, I don't like the name. There's a better name. It's called point slope form. This is just a formula. Where we choose any 2 points. I'm not going to go any further with that. I want to do slope-intercept form. Does anyone remember what a line looks like? It's y equals mx plus b. Because all we need to give a line in slope-intercept form is the slope, which is this one, and the intercept, the y-intercept, which is this one. So let's see if you're following. Very simply, what's our slope for this line? The slope is 1 over 2. X stays X. B, what's our y-intercept for this line, for this example? 1. So plus 1. That would be if I needed to give the slope of this line, that's how I would do it. Okay? So this is all one big example. It's not a general example, it's just an example. I'll get to the point soon. So just try to follow, okay? M here, of course, is a slope. I'm getting to a point. So the secant's also called the average slope. So if it asks you, if a question says find the average slope, then you get the secant line. Let's do an example so you can see what I'm actually talking about. Thank you. Oh, you put some special stuff in it, huh? It's just milk. Any sugar? You put just milk in it? What kind of savage are you? No, it's okay. Sorry. Emily. I guess we had to get rid of some milk, so she poured it in my coffee, but coffee with just milk. Ugh. Okay, where was I? Let's do this example. Sketch and find the slope of the secant line between x equals 1 and x equals 2. So we have a couple keywords. Find the slope of the secant line. So take 2 points, get the slope, and it says between these 2 points, between x equals 1 and x equals 2. So first things first, go find those points. I'm going to zoom in. Where are my points? My points are right here. When x is 1, my y value is up here. So I'm just going to label this. This is the point 1, 3. The point x equals 2. So x equals 1. X equals 2 is over here. You can probably tell me what the point is. This is x equals 2. That point actually is right there. So it's at the point 2, 0. And we get the slope. All right, nothing to it. Just go ahead and get the slope. I'm going to call it M is y2 minus y1, x2 minus x1. Which is -3. Anyone have a problem with that? And I mean, does that seem weird to you? Why I've done 0 minus 3 and maybe not the opposite? If so, it's because this is actually my first point. And this was my second point. We're going left to right. So Ablaziz, you nailed it. You can actually go backwards. I think it still works, but I don't recommend it. And it doesn't work for rise over run either. I'm going to erase this in a second. But just look at this. If you want to do it in shorthand, our 2 points, our rise is actually going to be 1, 2, 3, down 3. And our run is over 1. So it should be -3 over 1, which is our answer. Okay, so you can still do rise over run. I'm just showing you different ways to do it. There's no best way. It's just whichever way is easiest for you. Okay, so that's extremely important to be able to get that slope. But once you find the 2 points and use it, it's pretty straightforward. I think you should be okay with slope. I hope. 1 second, I'm looking at my notes here. I think this, just make a note here. This function, this should actually be a plus. All right, so there's a little typo in the notes. We haven't worked with that formula yet. There's a little typo, so just be careful, okay? So now that we have our slope, we need to find the equation of the secant line. How are we going to do that? Well, I'm going to allow you to use whatever method you want. I want you to use the slope-intercept form. You don't need to use it. Like I said, you can use whatever method you want, but I recommend you use this one. So we want the equation of the secant line. We know that our slope is -3. So let's just look at this. Do we know slope? Yes, we do. We know slope. Do we know the y-intercept? No, we don't. If we look at this graph, we can't see the y-intercept anywhere. So we need to find it. But we have y and x values. Just give me a x and y pair. So you know that we have 2 sets of numbers that we can use. We can use 1, 3, or we can use 2, 0. Which one do you want to use? It doesn't matter. Just put in one of those pairs. Pair 1 or pair 2? Going once, going twice. I'm going to use, it honestly doesn't matter. I'll use whichever one. Let's just use the first one for funsies. The y value is 3. The m slope is -3. The x value is 1. And the b. So no matter which pair you took, you'll still get that b is equal to -6. Because this is -3, bring it to the other side, it adds. If you took the second pair, it would be the same. It would work out the same. You would have 0 equals -3 times 2 plus b. You'd have 0 equals -6 plus b. You'd have 6 must equal b. Okay, so they would be the exact same. Now, what was the point? Some of you, sometimes when you get so far into a question, you lose track of what we were trying to do in the first place. So let me just try to recap. Sketch well, the sketch is done. Sketch and find the slope of the secant line. So we found the slope of the secant line. It's right here. We're done. And then the follow-up question was find the equation of the secant line. We have the slope, but we didn't have the equation because the equation is this, right? We need to fill out the pieces. It needs to look like y equals something x plus something. So now that we have b, I'll just call this like this is first step. Second step, just fill it in, substitute in what you know. So y is general, slope is -3, x minus 6. And we're done. Okay, that's our answer here, -3, x minus 6. Slope y-intercept. Questions? Any questions? We'll do another example like this just to make sure that it's clear, but that's the basic process. As usual, allow me to use my favorite tool in the universe, Desmos. And it really is, it's the most amazing, one of the best math tools out there. It doesn't matter what level you're at. Function is, my house is still getting moved, by the way, so there's people in my house doing stuff. Minus 6x plus 8. This is our function, okay? The reason I'm doing this, I just want to put the secant line that we found on it and see if it matches. So I'm going to put my points in. I know I had 1, 3. I know I had 2, 0. Those are my 2 points. You can see them here. And then let's go ahead and put our new line on it. And what should happen, and it's almost like magic in a way, if you understand how this math is working, our new line should go exactly through those 2 points. So we can kind of see if our solution is correct. Y equals -3x minus 6. I have a problem. What's the problem? Did anyone find it? Yeah. That would be great if that was a +6. I made a little mistake. Silly me. This is a +6. I really thought that was going to work. That was legitimate failure. +6, of course it's +6. And then this is plus. Okay, so my aha moment obviously was not as exceptional as I thought it was going to be. Of course the y-intercept is positive, like Yaya said. The y-intercept is up here. Wait a second. What is going on here? I think the function is wrong. This function here, maybe that was the mistake that was in the notes. Let me just double check here. I guess it should be 8. Anyway, for some reason this question was broken. I instantly regret trying to, oh no. Yeah. Sorry. It's early morning. My wife brought me coffee that has only milk in it. Give me a break. My point was, if you have a function and you find the secant line between these 2 points and you get the equation, it should go right through those 2 points, and it does. Okay, so sorry that I tripped my way through that, but it's still a pretty cool result as far as I'm concerned. And you can always check your answer if you're given the equation like that. So let's try to do a little bit smoother example. The other 2 ones you can try yourself. Actually, yeah, I don't know. I don't feel like I need to do a whole example. Let me just do part of this example. So it says for this curve, find the average slope. That means the secant line. Between x equals 2 and x equals 1. So what that means, just in case you were to get a question like this, I don't want to skip it. This is a slightly different type. When x equals -2, what is the y value? Well, y is -2 minus 1 over 2 plus 1. This gives us, let me just work out these numbers here. I didn't do this one ahead of time, but I feel like I made such a mess of the last one. I want to get this one right. This is -6. So we're going to have the point -2 and -6 from this one. All right, so just so you know what I'm doing, I have a function. I don't know what it looks like, but I know that I need the slope between 2 points on the curve at x equals 2, -2, and x equals 1. I also need to put in x equals 1. My y value at that point is going to give me, I guess that's a 3 over 2. So we have the point 1, 3 over 2. The reason I need to know what those points are is now I can get the slope. Sorry, my eyes itchy. Now we can do, we just need the slope. We don't need the line itself. That's the second part. So we just need the slope. y2 minus y1, x2 minus x1. y2 here is 3 over 2 minus -6. x2 is 1 minus -2. So just in case you're a little bit lost, let me color code these guys. Oops. What does that give us? I think if you work it out by calculator, you know, just any of the calculators you use should be able to figure this one out. 5 over 2. Okay, so a 3-step process. Find a point, find another point, get the slope between those points. Is that clear so far? That one was different because we didn't have the graph, but we're just substituting points in. Now we need to get the equation of the secant line. I'm going to follow the exact same process as I did before. The equation, let's remember, we need to solve y equals mx plus b. We're just going to use our slope and one of the points to solve it. So which point do you want to use? I think I want to use the one that doesn't have the fractions. Yeah, I'm going to use the first one. Like, this one's a little bit uglier. Why would you choose to put a fraction into your question? You know, why not put in whole numbers? So I'm gonna choose that one. That means we have -6 equals, I need to give myself some space. -6 equals our slope, which is 5 over 2, times our other x value, -2, plus b. We're looking for b. I'm running out of space here, so I'm just going to tell you that b equals -1. You can try that yourself, okay? Actually, just, I might as well be nice. Let me move it over. This cancels, becomes -5. Bring it to the other side. B equals -1. I just need to give myself space. I don't know who made this book, but clearly they didn't think ahead. So it was just spacing. What's the last thing I need to do? I need to take all of my pieces and put them in and make the final equation. Y equals 5 over 2 x minus 1. Okay, how's that? How does that feel? I'm going to graph it to confirm our answer, but the steps are clear, hopefully. Get your 2 points, get the slope, find your equation by solving for b. Hopefully that's okay. I'm going to confirm my answer. I have a good feeling about this one. I think that this is gonna be okay. It's all gonna be okay. Let's see here. I have the curve y equals x cubed minus 1 over 2x plus 1. Woo! What a curve. Now that's a curve. I mean, that is a curve. Do you know why it looks like that? It's because I typed it in wrong. I wish it was that curve. Makes me really sad that it's not. Plus 1. Okay, well, all right. We got a nice boring curve. Whatever. Let's label our points. We have the point -2 and -6. We have the point 1 and 3 over 2. And let's see. Is that right? Have I messed it up? No, I think we're okay. We should have made a line that goes through this point and this point. All right, we need a secant line that looks exactly like that. Well, not exactly, but at least, you know, better than that. Let's do it. Let's put it in. Y equals 5 over 2. Yes. It's the best day ever. We put a line through it. Okay. I feel better. I feel like I've accomplished something today. Maybe I can go back to bed. Anyone want to go back to bed? No? Just me? No one's typed anything for a while. Have I bored you to death? Are you getting it? What's the state of things? You know what I'm going to do here? I'm going to take a little screenshot. Put it right here. Just as a trophy for how cool an answer we just got. All right. No one's typing anything. I'm just going to go ahead and assume you're still alive. If you're not, please watch the recording after. The other one, you can do yourself. So we're getting slower, bit by, what am I trying to say? Bit by bit, we're getting closer to what it means to have a derivative. And the biggest problem here is that with derivatives, we need what's called a tangent line. And how do you get a slope of a tangent line without 2 points? So let me recap. Let me start from the start, actually. It says here, the actual slope of a curve, and by actual it means not the average slope or the like approximate slope, the exact slope of a curve is represented by the tangent line. So you can see here, it says graphically, the tangent line is the slope of the curve at 1 point, touches the curve only at 1 point, and is perpendicular to the curve at that point. So Desmos knows that most students doing math need to do this. So they already have this done for us. Let me see if I can find it. Under tangent line, yeah. So Desmos already has this made. What the tangent line means is it's the slope of this line. Wherever we put this point, we draw a line perfectly tangent to it, so that it only touches at 1 point, and then that's it, right? So we look at this line, we can see that it doesn't touch at 2 points, it touches at a single point. That's the tangent line. We can put it wherever we want. So let's just put it over here. In this case, it doesn't say what the slope is, but that's the idea. So at different points, we have different slopes. Of course, if we get the slope at this point, it has a really, really big curve, or sorry, big slope. At a different point on the same curve, we have a 0 slope. At a different point still on the same curve, we have a negative slope. In fact, I'm going to change this word. I'm not going to say big, I'm going to say positive. So this area has a positive slope, this area has a 0 slope, this area has a negative slope for the same curve. So how do you get one formula that can give you infinite number of slopes? It doesn't really make sense, does it? Thankfully, calculus, Isaac Newton figured that out a long time ago. So we'll get to that. Let me just make a little note here. Graphically, So if we look at the graph, tangent line, it's three things. It's the slope of the curve at one point. That's a huge difference. Remember, secant uses 2 points. B, it touches the curve only at that point, so you can see it only touches once, doesn't touch twice or 3 times. And it's perpendicular to the curve at that point. So what that means is that if the curve, wait a second, perpendicular, it's parallel to the curve at that point, really. It's in the same direction. So my point, because it always comes back to what the point is. The point is the secant line is an approximation. The secant line is only a best guess at what the slope of a curve is. The tangent line is an exact answer. The problem is the math is a little trickier. But we'll see that it becomes easier the further we get into this. It says tangent line is much more difficult to define, and it'll be the focus of this unit. We'll see that soon. Wait, where am I right now? Oh yeah, sorry. Hopefully you're still with me. It'll get slightly trickier and then it's going to get easier again. So let's look at this question. I've canceled out part of the equation, which is why I've got these lines here. Just you can cancel everything else. It just says draw a tangent line. Well, it's drawn for you. Sorry, the curve is drawn for you, and it wants you to draw a tangent line at x equals 0 and x equals 1. So let's look at this graph. Where's x equals 0? The x equals 0 is right here. Let's draw a tangent line at that point. So I'm just going to bring up a ruler and do it graphically. It looks sort of like this. You got to approximate it. That's my tangent line. All right, that's the best I can do with that. At x equals 1 on the same curve, it will have a different tangent line. At this point, the tangent line is much steeper. It looks more like this. So I'm just asking you to know the difference. Just basically, if you choose different points on the curve, you're going to have different tangent lines. All right? The big idea? Getting slope from just the tangent line is difficult. Because how do we get the slope of this? Can someone give me an idea? How would I possibly get the slope of this line if it only touches once? Anyone have any ideas? Anyone still alive? Okay, so when you say rise and run, what are our 2 points? What 2 points are we going to take? Okay, 0, 0. And you mean, so you mean you would take this and then choose another point on that line? So like this or this? Is this what you're saying? Yeah. So I think you can see one of the issues with it. It's because unless you draw it absolutely perfectly on the grid, it's difficult. Like, what is that point? You'd have to guess. What's this point? It's close to the intersection, but you'd have to guess. So immediately, our answer is only close and not perfect. You see what I'm saying? So we could do that. We'd still be guessing, but we want the exact slope. So the bottom line here is it's very tricky to do. It can be done, but there's a better way. And the better way is to actually use calculus. Use what's called derivatives to figure out the slope, and it'll be the slope the same. It'll give you the perfect answer every single time. All right, so I'm going to show you the big idea here. I've got one more burst of explanation I need to throw at you, and then we're going to be like into calculus. Okay? This connects tangent line ideas secant line ideas, limit ideas, all of this together. So I really need you to pay close attention, okay? If you were trailing off, doing your own thing, this is the time that you need to pay attention, okay? So this is the beginning of what is one of the most important concepts. Let me say this is a key concept. The tangent line. We can use the secant line to approximate the tangent line. And I'm going to show you how. Let me step you through it as easily as I can. First things first. Let's say we wanted the slope of this line. Let's just say I wanted the slope of the curve, and so I choose any 2 points here. Okay? We've got 2 points. I want the slope of that line, and so I'm going to draw a line through it. I'm going to do my best guess. And this is my secant line, okay? Let's just say I wanted to figure out what that was. Well, that would be a secant line, but really, what I really want here is I want the slope at this point. That's the slope that I want. Using the secant line, we can only get an approximation. So let me just show you something. Secant. We could get the average slope of that. You know, it's not quite what it should be, but we could do a pretty decent job. The tangent line looks very, very, very different. The tangent line actually looks like this. So we can see that the tangent line can be used to approximate the slope, but in this case, it would be totally different. I've chosen a bad example for tangent. I'm sorry. Let me just move it. No, I'll keep it there. But I've done a bad example here. Anyway, my point is, what if we wanted to get the slope of that tangent line instead of the secant line? Well, we would have to get the slope. So the first thing we do, we'll call this point x. And it has an x value. We don't know what the function is, but we know that it has an x value. And then we know that at this point here, yeah, I've done a bad, yeah. So sorry, I didn't want to erase this, but I am going to shift the point because as Mohammed said, the tangent line is 0. It's kind of not giving the example that I want. And so that was my mistake. I'm really sorry. I got to move this point over so that the example makes more sense. All right. For any of you who are writing that on paper, I'm really sorry. I'm sorry, but it's going to mess up the example unless I do a change. So I'm going to draw the tangent line first. Let me draw the tangent line. That's our tangent line. That's the line that we want the slope of. We can't get that slope exactly, so we're going to do our best by making a secant line. So choose 2 points. You all need to do this yourself. I'm trying to explain something. And we can say, look, those slopes are not the same, but at least they're close. I don't know what I've done over there. And I'll follow the same process. This first point, we can call that an x value, and it has an associated y value, which we call f of x. That's nothing new, hopefully. You know that functions are called f of x. Okay? The next thing we're going to do is choose a different value, a different x value. We're going to call this something. Because of the way we're going to set this up, we're going to call it x plus some small difference h, which means that the associated y value is f of x plus h. Now let's try not to get lost here. This is just terminology. We have some x value. We put it into the function. It's called f of x. Okay. So all I've done right now is said that it has 2 points. We could call it x1, y1, but there's a reason we do this. And we compare them. We actually need to get the slope of the secant line here. So what's the slope of the secant line? The slope of the secant line right now would be rise over run. And what's the rise here? Just bear with me for a second, I'm getting somewhere. If I compare the lines, this would be f of x plus h. This y value would be f of x. So the rise is actually those subtracted. And the run is x plus h minus x, which is actually h. So you can just believe me for a second that that's true. All I've done is said, I want the distance here between them. That distance is x, and the distance here is h. So there's a lot going on in this diagram, but I hope that you can make sense of what I've done. My whole point is that you can't get the slope of a tangent line by a graph, not with regular strategy. You can get the slope of a secant line easily. The problem is we want the tangent line, not the secant line. So let me show you one more thing, okay? I've made a Desmos thing for you, and I hope that it'll help. So let's look at this. We have a curve, a blue curve. Let me take off a few of the things. This blue curve is the curve that we want to get the slope of. We can see here that it has a tangent, okay? Look at the tangent here. At different points, it has different values. Let's just put it over here. It doesn't really matter where I put it. At that point, the tangent is about 1.22. Slope of the tangent is 1.22. And I'm just going to leave that there. We'll talk about that in a second. Let's use secant to approximate it. So we'll put 1 point right there. And look, those two lines, the purple line and the green line, purple line is the secant line. If we move the point around, we can get closer and closer to the tangent line. And the closer those 2 points get to the tangent, the closer the slopes are going to be. Look how close they get as I close the distance in the x values between the 2 points. The slope, look over here. The slope of the secant line right now, at this exact moment, can change depending on where the point is. Right now, the slope is very small because of the 2 points. As I get closer and closer and closer to the tangent line, it's going to get closer and closer and closer to 1.22. Do you see this? Right now it's 1.11. If I get even closer, it's going to be 1.16. If I get even closer, it's going to be 1.2. If I get even closer, it's going to be 1.21. If I get even closer, undefined, because I would be dividing by 0. So we got close, but not quite good enough. So I've actually broken this. I can move it though. All right, we can get close, but not exact. So if we were able to close the distance perfectly, close it to 0, we would be able to get the slope. What is our strategy we can use to get closer and closer and closer to 0 without actually getting to 0? Well, that's the whole point of limits. So let me recap, and then I'll introduce the most important part of this. Not the harder part, just the most important one. We use the secant line to approximate tangent. We do our best guess. The closer we bring the 2 points we're using together, the closer we'll get to the actual tangent line. If we can make the distance between them essentially 0, if we can get the limit as x approaches 0, we will get the actual slope. It'll be so close to the actual slope that it'll be the slope. So let me show you what that is. We can shrink the distance between the 2 points until x is actually 0. And it says this would actually be dividing by 0 because we'd end up making the distance too small. So I'm just going to say, hello, limits. Using limits, we can see what would happen. It would become 0. Look, the limit as x approaches 0 of our slope function would be the exact slope of the tangent line. The name of that is the derivative. Some of you have long since tuned out. This is a heavy topic, but bear with me. This over here is called the delta process. If we use the delta process, it will give us the slope of the tangent line, which is actually the derivative. It's getting the slope of between 2 points, but making the 2 points so close to each other that there's no difference between them. It just gives the slope at that point only, not between 2 points. It's not a secant anymore, it's a tangent. So the limit of the secant as x approaches 0 is the tangent. Okay, so let me show you how this works in practice. Okay, let me show you what we're getting at here. This will make it clear. So even if you didn't understand what we just did, I'm going to give you the recipe for how to do this. And this example is extremely important. So this is our recipe for how derivatives work. Are you with me? Can I just get a yes? Because I know that that was heavy. There's a lot of brain action going on. Can I just get a yes or a hi that you're still with me? Okay. Long story short, if you have 2 points, you have to get a slope between them. It can't possibly be a tangent line. If you bring those slopes, those 2 points so close together that they're touching, you'll only have 1 point. That'll be your tangent, and that'll be the exact slope. So that's what the delta process does. Let me show you the example. Estimate the slope of the curve, f of x equals x squared, at the point 1, 1. So this point here, 1, 1. Using secants at the point x equals 2 and x equals 1.5. So right away I'm going to change that. Those are terrible choices. Just write in this, x equals 1 and x equals 2. So it's saying we want the slope of the curve at this. So let me just show you the tangent. Let's try to draw the tangent at the point 1, 1. Tangent will look like, I'm going to say this. Sorry, it's tricky, but I'm trying to draw a line that only touches once. Okay, that'll be our tangent. And the points that it gave us are 1 and 2. I'm going to draw that secant line. That's our secant. You can see that the slopes are close but not perfect. So we're just going to get the slope of the secant way, slope of the secant the old way, and then I'm going to show you the new way. So what's the slope? The slope of the secant. The slope of the imperfect version of this, m, is y2 minus y1. So it's 4 minus 1 over 2 minus 1. That gives us 3 over 1, or 3. Our slope is 3 for this approximation. And again, this is the slope using the secant method. Okay? It's simple, it's fast, but it's not accurate. So I'm going to actually write this out because it's extremely important that you understand what's going on. This is just an estimate of the slope when x equals 1. Because that's, or maybe make it more specific, of the slope at the point 1, 1. It's just an estimate of the slope at that point. It's not the tangent line, it's just our best guess. I'm going to say, to be exact, we must find the slope of the tangent line. We must find the slope of the tangent line at 1, 1 using the delta process. Also known as the derivative. I'm going to show you how that works. But this is the idea. Secant, not great. Tangent, exact. Just a little bit extra work. Let's go ahead and do this, okay? Do you need any more time to write that down, or you can check it later on the video maybe? Just going to move on. Find the slope of the tangent at the point 1, 1. If it says the slope at the tangent, you need to use the delta process. Believe it or not, you'll probably actually enjoy this method. It's not hard. Even though it looks maybe the setup was complicated, you can do this method without even really understanding what you're doing. So the function here was x squared. If you don't know why, because this is the function we're talking about, x squared. The slope of the tangent line at that point, that's our function. The slope is the answer of the delta process. So the delta process is as follows. The limit as h approaches 0, as the distance between 2 points equals 0, of x at the second point, y value at the first point, over h. H is just a tiny distance between x values. And we're just going to bring it to 0. So one more step, and then the rest of it will be what we've seen before. This is our last step, probably the most important step. Take your function, x squared, and put x plus h in whenever you see x. So we're going to have x plus h squared minus x squared all over h. Okay. I'm not going to go any further yet because the rest is what we've done before. Do you know why I have that x plus h in there? At this point, it doesn't have anything to do with the approaching of 0. Let me try to write it out as clear as I can. Our function, I'm going to erase this, is x squared. We're just saying, look, I have two versions of this function. I have f of x and I have f, I'll put it to the side actually so I don't need to erase it. We have our function, our original function is f of x. F of x plus h is just the same function, but we've replaced x with x plus h. And then we can replace those up here. It's saying the function value at x and the function value at x a tiny bit over to the right. I'm going to continue so you can see the algebra comes out of this. Treat x and h and x like regular variables now. So the limit as x approaches 0, we need to expand this piece. So it's x squared plus 2xh plus h squared. That's from the brackets. Minus x squared over h. Does anyone need explaining what where that blue came from? It's just the expansion. Very good. Now what's going to happen? Well, everything starts to collapse. We have x squared, and x squared can cancel, and we can factor the rest. We have limit as x approaches 0. Factor everything you possibly can out of the top. That will leave an h. And if we go a little bit further, they'll cancel. And we end up with being able to do a direct substitution. I don't know how I got so sideways here, sorry about that. Okay. The thing about these questions with the delta process, it kind of gets worse before it gets better. We are going to do a little bit of work with this delta process. We need to know how to do it. But once we've got it all set up, we're going to do a bunch of shortcuts. That means we don't need to do the delta process to get the slope anymore. But you need to understand the delta process. It's based on this equation. This is the formula. All right. At this point, this was direct substitution. So how are we doing so far? Because I had to finish the question. We're almost done. I'm just going to keep on trucking. You might be asking, what the heck is going on? So Nasser, when you say the rest is difficult, do you mean the beginning part where we're comparing secant and tangent, or do you mean the expansion? Yeah. So let me try to give you just the basics. I want to recap it really quick. All you really need to know, okay, look at this green line. You can put it anywhere, but just look at the green line, this line. That's the tangent line. We want to get as close to that as possible using the secant line. So we take 2 points and we're like, okay, well, let's put 2 points that are really close to it and we'll be able to approximate it. But we want to make the distance between those two x values as small as possible. So the distance right now is h. Okay, that's what we call it. This distance between the 2 points is h. So if we make h 0, we will have the tangent line. If we make the distance 0, the slope of the secant line is the same as the tangent line. That's what the delta process does. So I'm never going to ask you, like, explain the whole secant and tangent process. All I'm going to do is ask you to use the delta process. Okay, I'm just going to ask you to use the formula. So maybe that'll help you relax. Maybe. All right, I want to finish the question. You're probably asking a lot of questions right now, but the most important question, I think, is why the heck did we do this? So let's go back up. We have our formula. This is our function. We did our best to get the slope at that point, and we got the answer 3. Now, using the delta process, this 2x can give us the slope of the graph at any point. So let me write it out clearly. This is the derivative of the function x squared. It's the derivative of that function. What that means, it can give us the slope of that of the function at any point, which is absolutely massive. That is a huge, huge, huge consequence. All right. That function 2x, we put any x value in there, it'll give us the slope of the original graph at that point. So let me show you what I mean. So for example, when x equals, no, the slope's not 1. When x equals 1, the slope is 2 times 1, which is 2. And that is much easier than doing it. I know there's some steps involved, but the idea is, what's the slope at the point 1? It's 2. What's the slope at the point 2? It would be 4. What's the slope at the point x equals 10? It would be 20. You have a function that gives you the slope at every single point on the graph. Okay, that's hugely important. It means that we can now have any function and get the slope of it. Let me show you the example clearly. Let's get rid of this crazy function here. Let me find the tangent, because this is helpful. Tangent line. The nice thing about this is it can take anything. X squared. So this is the function x squared at the point x equals 1. Oops. We know that the slope of that line, the slope of that line, that red line, is 2 right now. Because when x equals 1, the slope will be 2. We can change it. We can say, what about when x equals 10? The slope is much bigger there, obviously. So it's huge. So we just put 10 in. 2 times 10, it would be 20. The slope is 20, so it's really, really, really steep. I'll get more into that in another class. I've given you a lot to take in today. In fact, I think this is probably the most complicated concept left in the course. The rest, it's easier from here on out. Probably the hardest one to understand. But let me try to put you at ease. You can do the delta process without fully understanding the graph stuff, okay? Let me help you through this. So the delta process is called the definition of the derivative. It said previously we used limits to find the slope of the tangent at a particular value of x. Graphically, hopefully it made sense. Algebraically, by numbers, it's more useful to know the slope at any value of x. And in order to do that, you use what's called the delta process, also known as the derivative. You can see the previous page for the calculations of that. So it says for f of x squared, we know that the slope of the tangent is 2x. And we just put in an x value to give us the slope. That's from the previous page. This is called the derivative. Okay, let's do some quick examples. This is a function that gives us the slope of the tangent at any x. So when x is 0, what's the formula? Well, it's just 2 times 0. Which is 0. The slope at 0 is 0. It makes sense. At x equals 0, the slope is 0. What's the slope at x equals 1? 2 times 1. 2. So when x is 1, slope is 1. At x equals -1, we don't even need the graph. Just put in -1. We know the slope there must be -2. So these are our answers. All right? It gives us the slope at any point, no matter what point we put in. The function looks like this. It's telling us that at the point x equals 0, that there's just a little flat tangent here. It's telling us at the point x equals -1, the slope is negative. It's telling us at the point x equals 1, the slope is positive. This is what the function is doing for us. This is what the derivative is doing for us, telling us the slope at any point. How steep is the function, no matter where we look. And that is actually hugely important, especially for engineering, because it's also known as rate of change, which we'll do later. It can give us speed or acceleration of an object at any single point, if you know the position. Let me get to the point. The derivative is expressed as this. It's extremely important. It's called the delta process. There's different ways of calling it the derivative. The derivative of f with respect to x, or f prime of x, they all mean the same thing. They're all the derivative. Sometimes you'll see it like this, sometimes like this, sometimes like this, sometimes like this. They all mean the same thing. And when we do derivatives, we call it differentiation. But the most important thing I would say, probably in the entire unit, is this here. So this is the most important thing in the entire unit, possibly the whole of calculus, most important concept in calculus. Is that the slope of a curve is also known as the slope of the tangent line, and that is the derivative. The derivative is the slope of the curve. It's the most important concept. Let's do one more example, and then I'll release you from my shackles. Let me try to ease your mind that this stuff is not so bad. Okay? So clear your mind, take a moment, just, relax, think of happy thoughts, see if there's any clouds in the sky, We'll reset, and we'll finish one more example. So the delta process, or the derivative of a function called f prime. Notice there's a little nib there. There's a little, almost looks like a comma or an apostrophe, called prime. Is the limit as h approaches 0 of f plus h, f of x over h. Let's use that formula and find the derivative of this function here. So just so we're crystal clear, for this function, f of x is going to be f of x squared minus 1. F of x plus h is going to be 5x plus h squared minus 1. Let's use our formula. F prime equals the limit as x approaches 0 of what? Well, I'm going to use my formula. It's going to be 5x plus h squared minus 1 minus the original function. If you're not sure what I'm doing, this is f of x plus h. This is f of x. I'm just taking the original function, adding h to it, putting it back in over h. Okay, before I do anything else, because the rest is just algebra, is there anything I can re-explain for this? For this question. Let's expand it, see what cancels, and we'll have our derivative. We'll be able to give you the slope of this function no matter what. Let's do the algebra. Limit as h approaches 0. I'm going to expand the top here. 5 outside of x squared plus 2hx plus h squared minus 1 minus 5x squared plus 1. A lot of students mess that up. You have minus 1 times this and minus 1 times that. So be careful with that. Be careful. On bottom, we don't have anything different. So I'm going to see what I can cancel, if anything. And I see that I have a -1 and a +1. They'll cancel each other. Let's go one step further. Try to leave yourself lots of space. These questions get a little bit long. Okay, now that I've expanded this, we take another look at it and see if anything can cancel. And what I see is I have a 5x squared and a -5x squared. So they're going to cancel. Can anything else cancel? No. But I do have common factors. So the two-step process, I guess, is try to cancel everything if you can, and then once you've canceled everything, try to factor. So I'm going to try to factor out a common factor here. What I see is, let's see, what do I have in common? I can definitely see a h in common. I could actually see a 5, but it's not going to help me, so I'm going to take out the h. Cancel, cancel. It's the limit as h approaches 0 of 10x plus 5h. And then think about what we did yesterday. We can do direct substitution now. We do direct substitution, we get 10x plus 5. That's going to 0. 10x. So our derivative of the original function is 10x. That'll give us the slope of that function no matter where we go. We can put it in any x value, and it'll give us back the slope. So there's a lot of stuff in the middle, but usually functions, they get bigger, things cancel, and then they go back to this tiny little answer again. How do we feel about that? So, Abdulaziz, which part, I'm assuming we're talking about this, which part of this did we get lost at? You know, like step 1, 2, 3, 4, or 5. Three and 4. Okay. So you got lost somewhere around this point. Yeah. So what I did, it's really just, it's like algebra. Let me just make a side note here. I'm just going to rewrite. I'm going to just ignore the fact that we had h's, okay? It could be called anything. You can call it xy. Okay, and what we're doing, yeah, we're definitely going to solve the next one. I'll do one more example with you. I just want to show you that we're just dealing with algebra here. We're just saying, all right, I can see that there's a 1 and a 1, and we're expanding the brackets and seeing what cancels. Let's do one more. I think you'll probably start feeling more comfortable the more you see. All right, we'll do one last one. We need to do the delta process on this guy. We need to get the derivative of this. So the derivative, also known as f prime of x, is the limit as h approaches 0 of, I'll write the full definition out, right? So that's two different functions, but they're very similar. We just need to take x whenever we see it and replace it with f plus h, x plus h. So let me write it on the side. F of x plus h is the original function, but every time you see x, you replace it with x plus h. So I just wanted to put that on the side. Every time you see x, just replace it with x plus h. That's all we've done. It used to be x. It used to be x. Now it's x plus h. So I'm going to write that whole thing out. Subtract the original function. Okay, just so that we're all clear here. This function is this. This function is this. Divide it all by h. That's the hardest part. The rest is just algebra, and we expand things out and cancel as we can. But that is the hardest part to set up. If you can't set that up, you can't solve the rest. You know, you essentially would just get 0 on the rest of the question. How do you feel about that so far, Abdulaziz? I'm not trying to sing you out. I'm just talking to you because you were talking to me before. Okay. So what we're going to do is just use our algebra rules. This part here, we need to obviously expand it. This part here, we're just going to multiply through by 3. And for over here, we're just going to change the signs of everything. So we've got 3 different strategies. Okay, so this is 2 outside of the same thing it was before. So we start to see patterns in this. All right, plus expand that one. Multiply through. Minus 2x squared minus 3x. Once again, we're just multiplying through. It's an algebra exercise. All over h. It's getting a little close, so let me move it down a bit. Once again, we're going to multiply through. Some of you should be able to go on ahead and do this without me now, because it is just algebra. But of course, I'm going to do the whole thing. You see it now? You have the aha moment? Good, 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 good. I'm so happy to hear that. All right, I'm going to keep going. I can't do the limit yet because it's not in an easy enough form. Let's just keep going. They get big, but they end up being tiny in the end. That's when you know you're on the right track. All right, so once you do enough of these, they end up being kind of nice because you know you have the same process to do every time. You expand it, you cancel some things, you factor it, you cancel again. So let's see what can cancel. 2x squared, I see that twice. positive and a minus. I see a 3x and a negative 3x. Is there anything else I can cancel? And I am asking for actual purposes. I don't think there is, but I don't want to miss anything. Oh yeah, h. So I'm going to factor out the h. Let's go one step further and factor out that h. I don't want to skip too many steps. So there's a common factor of h. I'll take that out. Oh, there we go. We can cancel it. And now we can do the limit, because all we have left, we just need to get the limit of this. Limit as h approaches 0 of that. So all the h terms just get deleted, and we'll be done. Done. If you want a little extra work, I'll show you. It's the limit as x approaches 0 of 4x plus 2h plus 3. But really, this middle term will disappear. And this is our derivative. That's the function. That is the slope function of the original. If we take this function and graph it, we can use our derivative to tell the slope at any single point. Just take a point, you'll get the slope of it. So now we've got two nice examples done. How do we feel? Thumbs up? Can I just get a good, not good? Just get a reply, just so I can see that people actually made it to the end. Yeah, the same few people reply. So I think a few people probably jumped ship. Jump ship. Thumbs up. Okay, let me be crystal clear with you before we finish, okay? The delta process, the actual algebra part, once you work out some of the algebra, it's not difficult. The graph part is difficult. That's university level understanding, but I'm not going to be asking you very many questions, probably no questions on the graph part. So just relax, just worry about the delta process. Don't worry about the graph. I wanted you to be able to see the graph so that I've actually explained it, but don't worry about the graph. All you need to do is the delta process, okay? The last thing I'll say is that I've been marking the assignments. I said this on the WhatsApp group, but I'm really happy. Honestly, I think it's going really well. And I'm proud of you guys. I'm proud of all of you. You've been still working hard at this point in the term. Still got some energy. And I just want to say, thanks for still coming to class and putting your efforts into the studying, because it's difficult sometimes to stay focused. So good job to all of you who did that assignment, and I hope to get your marks back today. All right, I'm going to stop the recording here, actually. So bye-bye, see you next time. Fans.